One of the longest-standing questions in physics is, why is the electrostatic force 42 orders of magnitude greater than the gravitational force? This is known as the many orders of magnitude problem. In this episode, we shall develop an explanation for this phenomena, based upon the quantum vacuum's perception of each force. In our analysis, we utilize the quantum vacuum as the basis for comparison, rather than the traditional approach of a direct force comparison. This leads to the conclusion that the quantum vacuum perceives a 90-degree phase difference between these forces, yielding the well-known 42 orders of magnitude separation. So, let's get started. The first thing we'll do is look at the electrostatic force generated by charged particles. In order to achieve this, we need two charged particles, not just one. The reason we need two is because without a second charged particle, a force cannot be generated. We need to generate an electrostatic force because if we do not, we cannot relate it to gravitational force. Hence, we would have no basis to explain the 42 orders of magnitude separation between them. We need to relate forces to forces, and acceleration to acceleration. The reason we don't need two masses to model gravitational force is because, as general relativity explains, gravitational force is a manifestation of space-time curvature. Thus, a single mass is sufficient for gravitational force models, but two charged masses are required for electrostatic force models. Appearing on screen are two charged masses, separated by displacement r. Following the process arrows, we derive the standard physics representation for the electrostatic acceleration experienced by the small q charged particle. Let's now revisit the form of gravitational acceleration we derived in episode 1. Please review episode 1 if required. By invoking Einstein's equivalence principle and once again, following the process arrows, we arrive at a quantum vacuum frequency solution for the electrostatic spectrum. This denotes the frequency distribution of the quantum vacuum, induced by the presence of these two source charges. Notably, the quantum vacuum frequency lower limit, that is, the fundamental quantum vacuum frequency at r, is equal to the speed of light divided by the classical electron radius. We'll discuss this a bit more on the preceding slide. With the electrostatic spectrum derived, we're in a strong position to move forward. By recalling the gravitational spectrum derived in episode 4, we may establish the electrostatic to gravitational spectra ratio. As can be seen from the equation shown, the harmonic mode associated with both quantum vacuum spectra has evaporated from the solution, leaving only charge and mass. Evaluating the spectral ratio equation reveals the origin of the many orders of magnitude problem. Hence, we have shown that the many magnitudes of separation arises from the cubic frequency ratio between the electrostatic and gravitational spectra. It is important to remember that on the previous slide, we utilized Einstein's equivalence principle to relate electrostatic acceleration to gravitational acceleration, by utilizing the quantum vacuum as the common integration layer between them. This is distinctly different from the historical approach of relating electrostatic force to gravitational force directly, without transiting the quantum vacuum information layer en route to the solution. We'll look at this more closely on the next slide, but for now, we'll discuss the mechanical analog to the fundamental frequency, as appears in the illustration. We can see that, by envisioning an electron as a rotating sphere, the fundamental quantum vacuum frequency associated with electric charge is equal to the mechanical rotational frequency at the classical electron radius. This outcome provides reassuring evidence that our quantum vacuum-based solution does not contradict classical physics. Let's now close off the many orders of magnitude problem. As we have already established, the origin of the 42 orders of magnitude separation between electrostatic and gravitational effects arises from their spectral relationship with the quantum vacuum, in cubic frequency form, not from a direct force comparison as appears in classical physics derivations. Our electrogravimagnetic solution is consistent with general relativity because, as Einstein made abundantly clear in this formulation, gravitational forces do not exist within general relativity. What we perceive as gravitational force is in fact space-time curvature. Therefore, the many orders of magnitude problem is in a manner of speaking misrepresented classically. So, if our spectral ratio resolves the many orders of magnitude problem, what does the classical derivation of the force ratio tell us? Well, as we can see on screen, the classical physics derivation reveals a 90-degree phase difference between electrostatic and gravitational spectra. Or in classical terms, a 90-degree phase difference between electrostatic and gravitational forces. Thus, the quantum vacuum polarization induced by the presence of electrostatic charge is 90 degrees out of phase with the quantum vacuum polarization induced by the presence of mass. Moreover, the 90-degree phase difference between the electrostatic and gravitational spectra ensures that electrostatic charge is independent of gravitational mass. In addition, please note that these results support the conclusion derived in Episode 1, utilizing Buckingham pi theory. Let's now summarize what we've learned. The obvious lessons learned on our journey are materializing on screen. However, the most important fundamental concept we have derived is the importance of the quantum vacuum as a medium of common connection and energy exchange. We have shown that the origin of the many orders of magnitude problem is rooted in the quantum vacuum, as shown via the spectral ratio equation, not in the classical physics concept of forces. The force ratio equation tells us that the electrostatic quantum vacuum frequency spectrum is 90 degrees out of phase with the gravitational quantum vacuum frequency spectrum. Unfortunately, we cannot infer from these results whether the spectral phase shift is temporal, spatial or extra-dimensional in motivation. We know from previous episodes that the ground state of the quantum vacuum, that is the zero-point field, is a dark reservoir of quantum potential energy. It was also established that all forms of matter and energy will eventually be absorbed by the zero-point field in the far distant future. However, the physical universe also receives energy from the zero-point field, that is, the energy transfer process involves bidirectional photon exchange. This is an important realization because it means that the zero-point field acts as a common transaction account for all forms of energy over cosmological time. To emphasize this point, consider the following thought. Electron spin is a form of perpetual motion. As far as contemporary physics understands, electron spin does not run down, it's an intrinsic property of the electron. However, perpetual motion is considered to be an impossibility. So, how can we reconcile this collision of logic? Well, the answer might be that the electron somehow draws upon the energy contained within the zero-point field to sustain its intrinsic property of spin. Of course, this is not confirmed, but it's a plausible possibility. For viewers wishing to consult publications relevant to this episode, you may do so by accessing the links shown.